I'm going to talk a little bit today about what I work on mostly in my position in California, which is the process of fault creep. So I'm going to talk a little bit about what it is, how we find it, and what does it mean. So without further ado, I'll get into it. So part one of this talk is, what is fault creep? And the basic answer is that fault creep is slow aseismic movement of a fault, and where that fault interacts with human infrastructure, it will frequently damage it. So this is one example of a road in the city of Fremont in California, where the Hayward Fault runs right through it. You can see en echelon cracks, and you can see this is consistent with right lateral shear across this road. If you continue walking along this trend, actually, you'll see that the Hayward Fault goes through someone's house. This was not very well mapped before they built the houses. And that is a problem for infrastructure. One of the things that creep will do. And this is how creep was first discovered anywhere in California, actually. So in 1960, this set of papers was published talking about creep discovered on the San Andreas Fault. Here's a map of California showing where we're talking about. Essentially, this zone of the San Andreas, is known as the creeping segment now, because we have found creep all along it. But the first place that it was discovered was in a winery near the city of Hollister. And these three papers that were published in 1960 in BSSA really described the first observations of creep at this location, and potentially anywhere in California, I think. So the paper has pictures and has a map, shows where the fault zone is. There's that kind of trend there is the fault zone. It goes right through the winery warehouse. It goes through a drainage ditch here. And these are notable places. This particular picture here is taken of one of the authors measuring the offset in the wall down here due to the creep. So you can see more or less like he sat on one side, and then there's on the other side here, and there's right lateral shear through here. And basically, on the basis of measurements of benchmarks that he put in himself, he chiseled marks into the rock, into the concrete in the floor, and measured the growth of the offset over time. They were able to estimate a creep rate here of a half inch per year, which is 13 millimeters per year in better units. And they recognized that basically this had taken place over the time since the building was completed in 1948 up to when they started making measurements. There was an offset already in 1956. And with repeat measurements, they showed this trend and estimated it. And you can still go to this winery. It's kind of wild if you do, because there are plaques on the wall saying this is the San Andreas Fault. This is a national site of scientific interest. This wall, you can see, is actually broken. And down here, the concrete is actually shattered. And the internal walls in this building are offset from each other, which is cool. And you can go and take pictures of the outside. I went there in 2006 on a USGS-led field trip, and I went there again with my wife a few years ago, and we tried to reproduce some of the pictures. So you can see here, maybe right lateral shear. This whole side of the building is kind of blown out. So this is on the far side of the fault. This is the near side of the fault, and that damage is getting worse. The drainage ditch is also really, really clear. You can see in 2006, the channel is offset maybe by half of its width, and by 2021, pretty much the entire width of the channel is offset. So it's kind of buried under that grapevine, but you get the idea. This kind of thing was seen in other places as well. Once people really got their eye in, this is the sort of thing that happened on some major faults. Similar deformation was found on the Hayward Fault. This is in Fremont, again, the same city where I showed you the road picture from earlier. This is the entire interior of what is now a senior center, like a place for old people to go and hang out with each other. And there was a crack that goes through the middle of the floor in that building, and an offset in the wall. And then here in Izmit Pasha in Turkey, in a railway station, again, an offset in the wall that you can make out basically in the far distance there. So these deformations have been identified in lots of places now, and we're starting to compile a map of where they all are. And it's not just faults in California and Turkey that do this. Now we have found them in China, in Israel, in Afghanistan, Taiwan, and so on. So if, we have a growing inventory of them. It's partly, I think, an issue of detection. I think lots more faults do this. It's just that we don't have an easy way of finding them unless they intersect human infrastructure, in which case, we find that things break and it's very easy to spot them. But if you don't know where they are, it's a bit harder. And I'll get onto how we might use geodetic methods to find them in more places in a little bit. But once you know where they are, then you can study them in more detail. And the three papers that were published in that original set of articles about creep, there was one that measured offsets in stuff. So we've seen that one already, but there were two more, and one of them was using instruments to measure creep, and this was a crude creep meter, and I'll talk about those in a sec. And the third one was actually using geodetic methods to study the creep. So for creep meters, these are basically inexpensive instruments that you can bury in the ground across an active creeping fault and measure the movement of the fault. The idea basically is that you have these kind of stabilized vaults that are set up at an angle to the active fault trace, and you measure either the extension of this bar or cable that you stretch between them, or you measure the torque. The early ones measured torque, the later ones measure extension. The extension is slightly more stable, but they both give you basically an estimate of how the fault is moving over time. And so, for example, this study of a creep event in California, in Southern California, on the Superstition Hills Fault, uses a creep meter located here, and you can see that in this period from 2004 to 2007, there was steady creep for a while, and then a sudden rapid movement of the fault. And in detail, if you actually break that, if you zoom in on that first big movement, it actually is composed of many smaller sub events, and probably also you can see that even the steady movements are actually composed of small movements. So this creep kind of continues by small events. And you see kind of slower accumulations or slower sets of steady movements, and then occasional sort of surges of the fault and creep events. So that's one thing we know about them. And another thing we know about them is that you can study them over longer periods geodetically. And this is done mostly in California by sort of simple survey methods. So here is Forrest McFarland, who was a surveyor who made measurements of the Hayward Fault in particular for a couple of decades, and using a method that they call alignment arrays, which are really short baseline triangulation arrays. The idea is you set up your theodolite at this point here, and you have targets set up on one side of the fault and on the other side of the fault, and you measure the angle between this target and that target and how it changes over time. And you can calculate very, very precisely what the movement is from this setup. And one advantage of this is very low cost. The San Francisco State University had undergrads doing this for about 20 years, as well as some then professional surveyors later on. And so we have a very dense record of movements across various faults in the Bay Area of California, and showing interesting things. So one thing we note is that there are periodic movements of these faults. You can kind of pick them out in these two time series. So each creep event is when it sort of surges a bit, and then it does nothing, and then it surges again and does nothing. And these periods of stasis in this particular location are of the order of 3 or 4 years. But if you move a little bit along the fault to another section of the same fault, you can see creep events that don't tally with the other ones. And so different parts of the fault have different periodicities and are not necessarily in sync with each other. So there is a complicated set of behaviors that goes on. Another thing you can see is how these faults respond to other events. So this is a series of markers measured on the Southern Hayward Fault. Each one of them is tagged with how far along strike they are in kilometers. So like 68, 67, 66, 66. These are all in the southern part of the city of Fremont, again, the same place I showed you already on the Hayward Fault. And this record goes back at some locations to 1970 or 1969. I mean, it's quite an impressive record. But I want to draw your attention to some things that happened in the late 1980s and early 1990s. So this period here is the occurrence of the Loma Prieta earthquake. This is a famous earthquake in the Bay Area that happened during the middle of the World Series, which was between Oakland and San Francisco. So two cities in the Bay Area were playing in a baseball game, and an earthquake happened in the middle of the game. The coverage went black because the city started being damaged. It was like a really epic event. Its effect on the Hayward fault was to make it creep backwards for about 5 years. It's just interesting. This kind of suggests that the fault must be extremely weak frictionally for that to happen. It's not an easy thing to imagine, driving a right lateral fault left laterally for that period of time. And then one day in 1996, it moved forwards again pretty abruptly and caught back up to where it was supposed to be. So it was a large creep event in this part of California then. So there were interesting things that we can learn from these kinds of measurements. That it's a rich archive that we can look at for these sorts of things. More recently, I've had students who've been studying this area. This is my student Jerlyn Swiatlowski, or my former student, I should say. And we were interested in some kind of group participation event, a project where we could send school kids out to take photographs of curbs. And we did do that for a while. And then we thought we could also maybe try things like structure for motion photogrammetry and actually measure, like make models of these curbs and as they move. And we did that, and it was fun. So I'll show you one example of this. We have 2 point clouds here, a yellow one and a blue one. The yellow one is from 2016 and the blue one is from 2017. And what we have done is we basically aligned them we've merged these 2 point clouds on one side of the fault. The fault goes through here between two curbstones on a road. And if you look really, really closely, you'll see that the 2 point clouds are offset by a small amount. It's about 3 millimeters at this location. We could actually detect it. And we were able to use this to study the creep over a 3-year period on this section of the fault. And we found interesting kinematic things such as some years the movement was predominantly strike slip, and in other years there was a vertical component to the movement. And overall, it formed a velocity with an oblique rake, but that was not released steadily in the same direction. There was kind of complex kinematics to the fault zone. Anyway, I'd show it because it was cool, and yeah, I think underappreciated that you could actually do this you could monitor creep with pretty inexpensive cameras if you so wish. Okay, so why are we interested in this? Maybe it's nice, these faults are interesting. It's kind of an interesting intellectual exercise to study faults behaving in a way which is not expected. But there is a reason that it is still like very, very of a very great interest, the US Geological Survey, for example, and that is that you get earthquakes on these faults still as well. There are some famous ones on this compilation from Ruth Harris, or the faults in California. These are recent earthquakes, such as the Parkfield earthquakes, which are pretty famous as test cases, and a whole bunch of others. But perhaps the most famous of the creeping fault earthquakes that happened in this part of the world was the 1868 Hayward earthquake, which was a magnitude 6.7 and damaged buildings in San Francisco. That's what this is showing here. Destroyed the mission in San Jose, destroyed the courthouse in Alameda, and buildings in downtown Hayward. And actually caused the relocation of the original University of California, which was based in Oakland. It was destroyed in this earthquake, and they moved it to Berkeley. And they built it, of course, right on top of the Hayward Fault, actually, in Berkeley. But it's been over 150 years since that earthquake, and there haven't been another one. We do think the recurrence interval is probably of the order of 170 years. So that next one might be coming. And clearly, these faults this is the same fault, so it's capable of both behaviors, and we need to look into why and how this is possible. People wonder what causes creep, and we don't know for certain. It doesn't seem that there is a single mechanism that accounts for all examples. There are a couple of candidates, of course. One is some kind of lithological reason, some kind of property of the fault zone itself, potentially, the rocks in the fault zone. If you have something that's extremely weak and frictionally weak on the fault, that could cause the fault to move more freely. There are various candidates for what that could be. Some types of clay, like saponite clay, particularly, has been identified as one candidate. Serpentinites, in general, are capable of this kind of movement, and also talc has a low frictional coefficient. And various places in California, all of these things have been seen. So that's one possibility. And the other really is that it's something to do with pore pressure. One other way of weakening a fault is to weaken the normal stress on that fault, or the effective normal stress. And one way that you can weaken the effective normal stress is by having pressurized fluid in the fault zone. This has also been inferred in certain parts of the San Andreas fault system, for example. And certainly it's also been inferred in other environments, such as subduction zones. So what do we know about the separation of the locking behavior that might cause earthquakes, and creep behavior that we see damaging infrastructure on a regular basis? Well, we've had enough data collection now in some parts of Central California to start looking at this in a bit more detail. So this is the Parkfield segment of the San Andreas Fault, the southeastern end of the creeping segment of the San Andreas. And what's shown here is all the geodetic networks that exist in that area. So you've got triangulation networks that have subsequently been occupied with electronic distance measurements, which are baseline length change measurements, basically, that were made in the 60s and 70s and 80s, and then subsequently have been reoccupied with GNSS more recently. So we have all these measurements, and they go back to the 1930s. They span 2 full earthquake cycles of this Parkfield area. So what are shown here are maps of creep along a vertical plane that's fitted through this trace here. Red colors indicate slip, and blue colors indicate no slip. And this is the interval from 1934 to 1966, where showing in the north there is slip, in the south there is not. This is what happened in the 1966 Parkfield earthquake. The area that previously wasn't slipping suddenly did. Back to another interseismic period between 2 earthquakes from 1966 to 2004. Lots of creep in the north, lots of locking in the south. And then in 2004, there was another Parkfield earthquake, and it filled in the gap again. So whatever it is that in this location that is causing the creep and locking difference, I mean, it's persistent over multiple earthquake cycles, and it's confined to the same locations in the crust in the fault zone. So this raises the possibility that we could potentially constrain seismic hazard a little better by mapping where faults are moving. Then we can identify where they are not moving. And of course, where they are not moving interseismically is where the strain should be accumulating for future earthquakes. And of course, if we can also make maps like this, we can also potentially identify associations between the creep behavior and specific lithologies. So this is good for a justification for why we need to study this process in more detail from a hazard standpoint. Just also to say that this is not just a process or a phenomenon which is unique to strike slip faults in California and a few other places. You can also see similar types of separation of locking, or in this case, you would call it coupling potentially, in subduction zones. So this is the Nicoya subduction zone in Costa Rica. There is a very dense GPS network that sticks out basically over this earthquake source region located here. So there are 2 maps. This is a map of interseismic locking showing, this area of the subduction zone was basically locked, was not moving, or the 2 plates were moving together. And this is the slip that occurred in a magnitude 7.6 earthquake in, I think, 2012. Showing that basically the area where the fault was, the subduction zone was coupled most strongly, was the place where it slipped the most in the earthquake. So that, we could also maybe apply these kinds of ideas to studying asperities and earthquake sources in subduction zones. And I'm starting to do that with one of my postdocs. Anyway. So how do we find creep? Well, I'm going to offer a few possibilities here. I'm going to show you how we have done this with INSAR, looking at places in California. I've also could show you how you could do it seismically, looking for repeating earthquakes. And the third thing I'm going to show you is our attempts to do this in a larger scale. So we're trying to make a statewide model of creep for California, and I'll show you where that effort is currently at. So my bread and butter, my core business as a researcher is doing INSAR. INSAR is a method which is now quite mature. I always like to explain it though, just in case people haven't explained it. The basic idea is you have a satellite that's flying over the same places on the Earth's surface routinely, and emitting pulses of microwave radar towards the ground. And you measure basically the difference in phase between successive passes of the satellite. The phases are related to how far away the ground is from the satellite. So that each, and if the ground is to move, then when you difference the phase from the pass after the ground movement, the phase of the pass before it, you'll measure this phase change, which is associated with the motion of the ground and is proportional to the motion of the ground, the actual distance that the ground was displaced. So if you track that over long enough periods of time, you can actually measure velocities of movement of the ground. And what I'm going to show you here is a map of surface deformation velocity from the San Francisco Bay Area. This is data from the 1990s from the ERS satellites that were operated by the European Space Agency. So every single dot here is basically a time series of these movements, and the best velocity fit to that time series is what is plotted. And you can see there's all sorts of pretty colors all over the place. I'll point out a few features. One is that basically red colors, which are in this data set, indicate movement away from the satellite, and the satellite is pointing to the west. Those red colors are more common in the west and get progressively bluer as you move to the east. This is the motion basically of the plate boundary in this part of California. So red is moving with the Pacific plate and moving off towards Alaska. And red is moving towards Alaska, and blue is basically moving with the interior of North America. Okay, that's one thing. But there's a bunch of other things too. Here is a very large geothermal field called the geysers, the largest in the world, produces 700 megawatts of power, and still does. Produced 2 gigawatts of power at its peak, but I think was overexploited and has lost some of its capacity due to greediness of the operators of that geothermal field. There's a whole bunch of other features, some moving up and some moving down, that are related to groundwater. So red in this is moving away from the satellite. That could mean subsidence. Blue similarly could mean uplift, moving to the ground towards the satellite in this case. There's a whole bunch of red blobs around the edges of San Francisco Bay and San Pablo Bay, which are all related to compaction of muds. A lot of the land that is built on there is reclaimed. They basically just tipped rubble into the bay until they had some land to build on. And the mud that was underneath is slowly settling and compacting and causing things to sink. This location here is San Francisco Airport, for example. This is not necessarily what you want for your airports. But that's not what I'm interested in. What I'm interested in is features like this, where you see an abrupt transition in velocity between one side of a fault and another, and that is a manifestation of creep. And actually, this one here is the Hayward Fault. This is the kind of the Berkeley, Oakland area here. You can also see it's also happening on this fault over here at the Concord Fault. And what I've been trying to do for probably the last 15 years is see how far north on the other faults this creep behavior persists. And so one place I've looked is the Rogers Creek Fault, which is located here. This is wine country in California, so it's a great place to do fieldwork, turns out. And it turns out also that I think it's creeping. So you can see a transition from yellow to blue across the fault here, and that is probably a creep signal and has been confirmed more or less by repeated field observation and more INSAR data. So we can do this using these days the Sentinel-1 satellites, which are a newer mission that has more routine observations in California every 12 days there. And this allows us basically to get better signal into areas where previously it was less promising. This is work that my student Jerlyn did with David Beckert from JPL. And we are looking now at the Rogers Creek and Markham faults. Whoa, I keep advancing by mistake. And this goes off for another 150 kilometers basically into the forest in Northern California. So it's into places where it's much harder to do INSAR traditionally. What you can see is that there are still abrupt changes in color across these faults. I'm showing both ascending and descending data here. So the flight direction of the satellite is different between these two. One is looking to the west and one is looking to the east. And so what you should see, and what you indeed do see, is that the sense of color offset reverses between the descending track and the ascending track. Here there's red in the west and yellow in the east. Here there's yellow in the east and red in yellow in the west and red in the east. Yeah, so the sense is reversed. Unfortunately, the color scheme was also reversed from the plots I showed you before. So this big blue blob is the geothermal field that I showed you earlier. It was a big red blob in the data before. And this just goes to show that INSAR people are very inconsistent with their color palettes. And this was all made by Jerlyn before I told her to use the other sense of motion. Anyway, just take it from me, it is moving right laterally and not moving backwards and all that, and we're all good. And what we do is we take the velocities, we take profiles through them, and then we fit basically straight lines to either side of your profile and estimate the offset between them, and that gives us an estimate of the surface offset rate that we can relate to a creep rate. And when you do that, in for example, the southern Markham fault, you can see that there are a series of resolvable steps in the time series in the velocity profiles that show basically that these faults have an offset that's moving. The ground is being offset at the fault itself. And you can also see that the sense of the offset reverses between the descending and ascending data, showing that it truly is a horizontal movement of the ground. If they had both the same sign, then you would say this was a vertical movement of the vertical offset of the ground, because they both point downwards, but they point downwards in opposite horizontal directions. So if you see a reversal in the offset between the two data sets, that means it's moving towards one and away from the other, which means it has a component of horizontal movement. So we can measure our fault movement rates, and we get 2 millimeters a year along the Rogers Creek fault. So it is creeping, like I said it was. You get a bit more along chunks of the Markham fault, and then you get this surge of faster creep on the Markham fault in this location here. And interestingly, this is the part of the Markham fault that is really close to that geothermal field. So has raised the question in my mind: are they physically related somehow? Is the geothermal activity, the human activity in the geothermal fault, actually changing the stress on the Markham fault? And I have as yet been unable to prove that, but I am trying to look at the possible connection. Okay, so that's INSAR. What else can we do? We can also do seismic things to study creep. So this is kind of maybe counterintuitive in a way, using seismic waves to study an aseismic process. But the basic idea is that even on a fault which is moving aseismically, it's not entirely homogeneous in terms of the frictional behavior of the fault. We can and we do identify earthquakes that are localized on the fault surface when we look at these faults. And what we think these sources are basically parts of the fault which maybe have a slightly different frictional property that are getting dragged along by the creep that is occurring around them. So they're continuously being reloaded to failure and then failing. And if the creep rate is constant, then the recurrence rate of these earthquakes should also be constant. And we do find cases where that's true. So, for example, this is work done by my former student, Nada Shakabai Sinabari. If you have all things being the same between earthquakes on a fault, so if the source location is the same and the path for the seismic waves to the instrument being the same and the source process is the same, then the earthquake waveforms should be the same. And we find that they are. So this is a series of earthquakes that happened on the Rogers Creek fault. They have a periodicity of somewhere between 6 and 7 years in that range. And we see that they have basically identical waveforms. So this is what we call a repeating earthquake sequence. And if you can identify these, then you have markers of potential creep on a fault, because the periodicity and the similarity is very, very unique to this type of earthquake. So we did this study of the northern Bay Area, so north of San Francisco, off into the forests towards the Mendocino Triple Junction, where there's a change in tectonic behavior. looking at all of the earthquakes that occurred in this area and comparing them to each other to figure out how many of them were repeating. So there were 75,000 earthquakes that happened in this region between the 1980s and the early 2020, the late 2015, 2016 kind of time. We had 670,000 waveforms recorded at 350 stations, and we did a big data mining cross-correlation effort to compare all these things to each other to find out which ones were repeaters. Along the way, we found ourselves having to write codes that did efficient, fast cross-correlation for the three seismologists in the audience. Maybe we have a code that's called super efficient cross-correlation. It works very well in MATLAB on desktop machines. No, I wanted to call it this because its acronym is sexy. I apologize for that. That's terrible. But basically, it does work very well. You concatenate all your waveforms together. You have your templates in another waveform, and you just compare the template to the whole concatenated waveform all in one go. And even though you're comparing a bunch of things that don't make any physical sense, it's still faster than looping one by one through the earthquakes and doing the comparison that way. Anyway, what we found was that we could identify repeating earthquakes, and even though the network was changing over the period of our study. So unfortunately, this part of California has a variable network quality over time. Stations come in and go out or get their components renamed. It was kind of annoying. But we found that we could still assemble families of repeating earthquakes based on pairwise similarity. So we could say that earthquake A and earthquake B were very similar to each other, and earthquake B and earthquake C were very similar to each other. And so assemble a family of repeaters that way, even though very few stations would record A, B, and C together. So that's basically what's shown here, that there are 3 repeating earthquakes out of the 11 sources that are in this particular location. And these are all the stations that detected them. We've color-coded the waveforms to the events. So you can see, purple and red are identical at a bunch of these, red and purple and blue at a bunch of others, and red and blue at some others. There's only one station that recorded all 3. And that's this one. But we're able basically to use the similarity at all these other stations to build this kind of family tree of similarity, which is what's shown here. So yeah, this is how we built our catalog of repeating earthquakes. And we found over 100 in this area, and they form along the Rogers Creek Markham fault system. They form over this fault system too, which is the Bartlett Springs Green Valley fault system. They do not form in this part of the world over the San Andreas. There are none. And in some cases, if we had a good record that we thought was complete and had showed good periodicity, we felt confident enough that we could estimate a slip rate or a creep rate based on basically the size of the stress drop at each event and relating that to slip. And estimating the slip rate that way. And we get rates between 2 and 6 millimeters a year on some of these faults. We see that basically where there is seismicity on the Markham fault, we have repeaters. Pretty much there is this big streak of seismicity that goes along the center of the fault at depth. And we find a bunch of repeating earthquakes along it. And if we look at specific locations, we can take profiles through the locations of our repeating earthquakes and learn something about what's going on there. This is the city of Willits, which has creep at the surface. This is my right foot on the Markham fault, showing this curb offset here. It's one of those places where there's a bunch of houses, buildings, walls, street signs, like lampposts that are all being mangled by the fault as it moves. The surface offset rate here is estimated to be about 5 millimeters a year. GPS that has a wider aperture measures 10 millimeters a year, suggesting that maybe it's not all on this one strand. And the earthquake evidence definitely suggests something similar. So we look at some profiles. You can see repeating earthquakes form some dipping trend that dips along with the seismicity at about 60 degrees. This is the surface location where my foot was, and is where the repeaters are down there, and 60-degree dip through that. Down here, you can see, again, some dipping structure, but there, the repeating earthquakes form more of a vertical trend. So it looks for all the world like actually these faults are splaying off. One is dipping at an angle and the other one is vertical, sort of splaying off of it, like so. And if you look at the landscape in this area, this is above the city of Willits in Google Earth, looking to the east, there is this fault scarp out here that is known as the East Willits Fault, and it's not a very well characterized fault. There is one master's thesis about it, but it does plot exactly above where our repeating earthquakes are. So we suspect very much that there is this kind of more complicated fault structure in this part of the world that we can get from the repeaters. And I have currently a student who is trying to do this kind of repeating earthquake analysis for the whole state of California. And we have done all of Northern California, where the data are very easy to download. And now we've run into trying to download data from Southern California, where it's all on the cloud using AWS. And we have a whole bunch of problems downloading the data from there, but we're working on it. Anyway, in the meantime, I've been looking at INSAR statewide as well. So one of the projects I work on is with people at JPL trying to make these kind of maps of the whole state of the deformation. And that's what's shown here. We have basically cover the whole of California. You need 4 ascending tracks of Sentinel-1 and 5 descending tracks. These tracks all overlap. They're kind of shown in this kind of exploded view. Really, they should overlap by half. So you can see, this feature here is actually located there. Whoa, come back. And there's a couple of things that are really obvious in this data set, I think. One is the creep on the San Andreas Fault. You can see this really sharp color change there. It's also really obvious here. And then this really large subsiding signal over the Central Valley of California, which I'm sure Christelle could tell you a lot more about if you ask her. It's a huge deformation signal. It's of the order of 10 centimeters a year in some places. It way outstrips our color palette that we're using here. So this is work I did with Sim Sanger and Marin Gavorchin from JPL. And what I've been doing is basically taking this amazing velocity data set and doing these same sorts of profile analyses that I showed you before. So taking a little box over a part of the fault. So for example, here, looking at the ascending and descending data and fitting basically lines to estimate the profile offsets, and then converting those into a creep rate. So at this particular location, we see a big negative offset in the ascending data and a big positive offset in the descending data. And that relates to a creep rate of about 18 millimeters a year, right lateral in this location. And I've done this for the whole state. So here are all the major faults in California. They are color-coded by, red and blue. Red would be right lateral slip. Blue would be left lateral. That some of these faults, for example, this is the Garlock fault here, is a left lateral fault, but it's not creeping. You can see there is creep in the faults in the north, there's creep on the central San Andreas, and there may be some details of creep down here. I will show you in a bit more detail. So, for example, the central San Andreas fault and its neighbor, the Pisces Calaveras fault here. If you look just along here, what I've shown is the ascending and descending offset rates, the vertical rates, and at the top here, the right lateral creep rates. And you can see that the creep goes up to about 28 millimeters a year. It's really reasonably self-consistent as you drop down to the south towards Parkfield and into the city of Chelam, which is where we think the San Andreas starts to be locked. That's where we think the last earthquake on the San Andreas fault in that location, the last big one, ended in 1857. So 28 millimeters per year, and that is consistent with estimates from GNSS, so that's all good. We can go to the central part here, north of Los Angeles, where we thought these faults were locked, and we're pretty sure that we were right when we thought they were locked. There is absolutely nothing to see in much of California. It looks like this, kind of boring. These faults are locked. There is no offset. There is nothing. But if you go far enough south again, you start to find interesting things. The Superstition Hills fault, which is where the creep meter I showed you was, that's creeping, which is great. The Imperial fault, which is the main plate boundary fault as you go into Mexico, that also is creeping, although the data's a bit messy. That's because there's a lot of agriculture there that screws with our ability to measure it. And maybe the most interesting thing that I discovered from this was that in the Coachella Valley, this part of the San Andreas fault, which is a bit away from where people inferred creep before, we have persistent and consistent and very nice and tightly defined offsets in the data around there that extend where we think the fault is creeping in its southern end quite a ways north. So we get 3 millimeters a year of creep for this segment up here. And we'd only previously seen it really around the north shore of the Salton Sea, but it extends another 30 kilometers or so to the northwest from where we thought it was before. So this is fun, and this is what hopefully we will combine this with a repeating earthquake map of the whole state and actually make a full comprehensive creep model for the state, and that's what I've been working on lately. Okay, so I have a few more minutes to talk about what does this all mean, and there's a couple of things I'm gonna get into. One is like, how can we tell how much of a fault is actually locked? That seems to be an important thing to know if you want to use this for seismic hazards. And I also will touch on frictional properties of the creeping fault areas. And this is a kind of a foretelling of that. This is a picture of the Bartlett Springs fault in Outcrop with a big, interesting gouge zone, which is very different from the materials on either side. Anyway, so one thing that you can do, and this is something that I did very early on, being someone who liked to model earthquakes, I can use a lot of the same inversion methods to study the creep. So we can take our INSAR data downsampled onto a grid. We can take GNSS data. We can take the data from the triangulation that was measured at the surface, the estimates of surface creep rate, and we can invert them to get some kind of map of slip on, this is the Hayward fault. And this is showing the Hayward fault model in a bit more detail. There are several really clear features. There's a lot of creep in the north and south, but not very much in the middle. So this area, magenta, is the area of low creep rate. And it's quite consistent actually with the location of the surface rupture from the 1868 earthquake, which went from Oakland to Fremont, more or less. There's also a data gap in the north, so we won't talk about that. But there's back up. There's high creep rate in this area, up to about 6 millimeters a year, and also down here, which is the city of Fremont, where I showed you already quite a few examples of surface features of the creep there. Another thing I have is a model which is a bit more sophisticated. So this is a boundary element model, and you can choose areas of the fault that you lock and calculate the slip on the rest of the fault based on an assumption that the frictional strength of the rest of the fault is 0. And you get some estimate of the creep on the rest of the fault. And basically, this model runs as a kind of a Markov chain Monte Carlo process. You keep adding fault elements or taking them away until you have a configuration of locked elements that fits the data well. And what you're seeing is basically over time, the model accumulates a lot more locked elements in the middle, and it loses them at the ends. So showing basically the north and the south parts of the fault are close to 3D creeping, but the central part of the fault is locked. And out of this, you eventually get a number of realizations of the potential locking distribution of the Hayward fault. And so what you can do is you can look at the statistics of that ensemble of locking distributions and draw inferences from them. So for example, here, areas that are red are basically locked in 0 models. Areas that are magenta and blue are locked in a high proportion of the models, and areas of the green are locked in about 50% of the models. So what you see basically is that we can mark out pretty well in the north and the south where the fault cannot be locked. And then it's a lot more difficult to say definitive things about the locking distribution in the sort of the blue and green areas. The blue definitely are locked most of the time. The green are locked about 50% of the time. So there is still some ambiguity here, unfortunately. We can't image it perfectly, but we have a sense of where the locking should be. And it's actually a bit shallower than in the kinematic model. And we can also use the statistics to estimate just how, on average, how much of the fault should be locked. And in this particular case, if you do that calculation, we can look at the southern part of the Hayward fault, and we estimate that it's about 25% of it is locked on average in our models, and we can estimate kind of uncertainties in that. And if you were to move it at its long-term slip rate, which is about 1 centimeter per year, we can estimate how much seismic moment has been stored in that part of the Hayward Fault. And equivalent, if an earthquake were to happen today, it would be of the order of magnitude 6.6. And given that the last one was a 6.7, this should start drawing people's attention to the fact that we are getting close to the time when it's reloaded for a repeat of the last event. So that's something that I'm working on still. Again, trying to make this type of modeling more efficient, and also looking potentially to see if there are any changes in the locking distribution over time, as some people have suggested. As you move through the earthquake cycle, the locking becomes more focused potentially. So we shall see. I'm working on that right now. So the other question, of course, is like, why does this part of the world have so much creep? And I'm looking again at the area north of San Francisco. So San Francisco is right at the bottom of this map, down here somewhere. Why is there so much creep here? Well, if you look at the geological map, there's a lot of purple on it. Purple on this map is ultramafics. California, as you may know, is basically an area of accretion through the Cenozoic. There was subduction originally under the state, and lots of stuff got scraped off of the downgoing Farallon plate and glommed onto the edge of North America. There are ophiolites throughout this zone, and this is where the serpentinites come from. And if you look in some places, so for example, I'm going to show you an outcrop of the Bartlett Springs Fault. This is a place where we know it is creeping, both from GNSS, INSAR, and also repeating earthquakes. This dipping fault trace here has a shallow repeating earthquake sequence. We also see it in INSAR and the deep repeating earthquake sequence. So top to bottom, it could be creeping here. And on the ground, you see an outcrop, and it's this gray slug going through more quartzo-feldspathic things. So we have basically a gouge which is rich in. There are two generations of gouge. There's an earlier one and maybe an altered one, as far as we can make out. The lighter colors are antigerite serpentinite, and the darker splotches are areas of tremolite, chlorite, and talc. And Jerlyn, my student, she went off to work with Diane Moore at the USGS, actually to work on natural samples of this gouge in a triaxial press apparatus, trying to smear sort of blocks of granite with the gouge material, and then driving them at different speeds to see what the frictional properties of the gouge were. And I am not an experimentalist by any means, but I can try and explain what we see. So this is a graph of a frictional coefficient on the y-axis and displacement. So the actual displacement of the rams that are driving the movement on the samples. And there are a series of different speeds shown here of slip. So it was originally moving at a tenth of a micron per second, and then slowed down to a hundredth of a micron. And when that slowdown happened, the velocity, the frictional strength went down. And then they sped it up again, and it went back up. They sped it up more, and it went up a bit more. They slowed it down again, it went down again. They sped it up again, it went up again, up and down, up and down. The fact that the changes in frictional strength occurred in the same sign as the changes in velocity imply that this material is velocity strengthening. In other words, friction goes up as you try and move it faster. This is actually a property that lots of people have suggested is critical for sustaining creep, because basically if you have something which gets weaker as you move it, velocity weakening, that drives you towards unstable slip. It makes it very much easier for slip instabilities to propagate and establish. Whereas if it always is trying to resist movement as you try and move it faster, it's kind of self-regulating. It's like a negative feedback. And so your creep never really gets unstable. It just kind of peters out. And that is why creep is often thought, it's an explanation for why creep is episodic as we see it. But basically, it can't get unstable and continue accelerating. It always slows down. Okay, and then why then do we see it in such a localized fashion? Well, Diane Moore and her colleagues at the USGS they've been doing geophysical surveys of this area and trying to infer like the locations of these serpentinite bodies and other ultramafics. And their canonical model that they're using for this is that basically the serpentinite material is injecting along the major faults. We know it's mechanically weak. We know it does actually squeeze through structures in other places. So this is their working model for now, at least, is that the Bartlett Springs fault which is where this gouge sample came from, and the Markham fault, which is the one to the west that I've been looking at mostly, are both sort of tapping into this coast range ophiolite material at depth, and that material is plating the fault zone somehow and allowing these faults to move aseismically. Okay, so that was a lot, but I don't have anything else to say. So if I have conclusions, they are basically that we the more we look within SAR with better data, the more creep we see in California. The Markham fault does look like it's creeping along most of its surface trace, for example, and we also find repeating earthquakes along most of it as well. The Hayward fault is creeping, but has about a quarter of its surface that is locked and accumulating strain for the next earthquake. And we see a putative association with surface expressions of serpentinite gouges along many of the faults that we think are creeping. And that's at least one of the explanations for why it's happening here. Thanks for your attention. I'm happy to take any questions.